Welcome back to Applied Algebra and Trigonometry. Today we're going to talk about the sum and difference of cubes, or rather, factoring the sums and the differences of cubes. So here is a sum of cubes, and here is a difference of cubes. Any number raised to the third power is called the cube of that number, or of that base. First, let's examine how we would factor the sum of cubes. But allow me to make a distinction. In each case, these formulas only work if we are talking about the sum of two cubes or the difference of two cubes. Once again, I want you to remember a pattern for factoring these. So I'm going to rewrite my a cubed plus b cubed here. We have the first term, a, that is cubed. So when we factor this, we're going to take that base, a. We're going to keep the sign the same. So we're going to add b to that. That's our first term. How do you factor the sum of two cubes? You factor it into a binomial and a trinomial. So for the next part, actually, I don't refer back to the original expression now. After I have this part factored, I usually refer back to the factor rather than back to the original binomial expression. So I take the first term of my factor and I square it. Then I change the sign to the opposite. I multiply the first term times the second term of my factor. And then, always positive, I always add the last term of my factor squared. So what I have is the same sign here, the opposite sign here, and this is always positive. And there's a fine mnemonic for you. Mnemonics are well and good, but they don't mean a thing if the rule is not true. So let's check to be sure the rule is true. I will be distributing every term in the binomial to every term in the trinomial. A times a squared gives me a cubed. A times negative ab gives me negative a squared b. A times a positive b squared gives me ab squared. Now I'm going to line up the next multiplications that I do so that they are easier to add in the end. So I'm going to multiply b times a squared. Those are both positive, giving me positive a squared b, because order does not matter if I'm just multiplying. Then b times negative ab gives me negative ab squared. And then b times positive b squared gives me positive b cubed. And look what happens. All of these terms add to give me 0. And I only have a cubed plus b cubed left, which is the binomial, the sum of two cubes, that I factored. So yes, that rule works. Let's look at what the difference is if we're dealing with the difference between two cubes. Will my SOAP mnemonic still be useful? So I take the cubed root of the first term. I keep the sign the same. I take the cubed root of the second term. Now I'm going to refer back to this binomial factor as I build my trinomial. I take the first term and I square it. I take the opposite sign. I multiply the first term times the second term, and then I add, because it's always positive, the last term squared. I applied my memory aid, SOAP. Let's see if it is valid. When I multiply my factors, I get a cubed plus a squared b plus a b squared. Then I get minus a squared b minus a b squared minus b cubed. And when I add all of these terms add to be 0. I get a cubed minus b cubed, which is what I started with. That's what I factored. So here are the patterns for factoring the sum of two cubes and the difference between two cubes, which would be appropriate to use for this problem. We have a cubed here, and yes, we do have a cubed here. It is sometimes helpful to rewrite the expression before you try to factor it. To factor this, I take the cubed root of the first term. I keep the sign the same. I take the cubed root of the second term. For my trinomial, take the first term of my first factor and I square it. I use the opposite sign. I multiply the two terms of my binomial factor, and then, always positive, so a plus, I square the last term in my binomial. And usually this is rewritten in this fashion, r plus 3, and we just usually put the coefficient in front of the variable so everybody knows what they're looking at. And there it is. Ta-da! Let's look at this expression. Can we factor it? I have rewritten the expression so it is clearly the difference between two cubes. I take the cubed root of the first term, I keep the sign the same, I take the cubed root of the second term. Now referring back to that binomial factor, I square the first term, I take the opposite sign, I multiply the first term and the second term, and then I add the last term squared. Let's look at example 3. Okay, 250s cubed. Let's see, what's the cubed root of 250? I don't know. Now maybe 250 doesn't have a cubed root. So before you start racking your brains trying to figure that out, first and always look for the greatest common factor. And the greatest common factor is only 2, but that does help some. Okay? Now, we have 125. Let's see, that's 5 cubed. So I can go ahead and write that down. 5 cubed times s cubed. And then 27 is 3 cubed and t to the 6th. All right, so some of you may be able to do t squared cubed just fine. But if you're a little concerned about whether you'll get the exponents mixed up, here's what you can do. Pick a new variable. I chose w, and I let w equal t squared. And now I have 2 times the difference between two cubes. And I'm going to apply the formula. 5s minus 3w times 25s squared plus 15sw plus, for always positive, 9w squared. I am almost done, but I have to return to my original variables. So I will need just a little more room. So here you see that I have substituted t squared for every w, and I have done it within parentheses because there's one last thing I need to do. To write this as clearly as I can, try to remove as many parentheses as I can. So I can remove the parentheses around t squared in the first term, in the second term, and in the last term by multiplying my exponents. There. That is the complete factorization of 250s cubed minus 54t to the 6th. Do not drop the greatest common factor. Let's see if we can factor this expression any further. Be careful. That first factor, b cubed plus 4, may trick you into thinking it is the sum of two cubes, but it is not. 4 is only a square. So we can't do anything with that right now. We just have b cubed plus 4 as one of our factors. However, the next term is the difference between two cubes because it is 2b cubed minus 1 cubed. Let's factor it. Let's leave our b cubed plus 4 as is. Take the cubed root of the first term, keep the sign the same. Take the cubed root of the second term, and then square the first term of my new factor there. And I am going to take the opposite sign. I'm going to multiply the two terms of my factor, and then I'm going to square the last term, keeping it positive as always, always positive. I haven't been checking my work, so let's do that. I did not touch b cubed plus 4, so I'm going to leave it alone. I'm just going to put it here in parentheses, and then multiply the rest. And sure enough, 4b squared and negative 4b squared give me 0, plus 2b and minus 2b give me 0, And I'm back to the quantity b cubed plus 4 times the quantity 8b cubed minus 1. Let's look at a fifth example. Our first term is no longer a simple single term cubed or a multiplication cubed. It is a sum that is cubed, but that is still considered one term because it's in parentheses. And what's in parentheses is cubed, so we do have the difference between two cubes. Let's follow the formula. The cube root of the first term minus the cubed root of the second term. The first term squared. We're going to take the opposite sign. We're going to multiply h times h plus t. And then always positive is the last term, which will be h squared. Now let's simplify. If we remove the parentheses inside the first term, we can see that's going to simplify a lot. Let me go ahead and take it down to the next step to show you that. There it is. H minus h is 0, leaving you just t and whatever else we have here. So let's see what we have. If we square h plus t, that's multiplying h plus t times h plus t. Do not try to bring that squared in. H plus t times h plus t will give me h squared plus 2ht plus t squared. All right, my next term here will give me a positive h squared plus ht, and then I have positive h squared. All right, let's combine some like terms within those parentheses. All right, looks good. We are finished because that trinomial that we have left as a factor will not itself factor. So that's the answer. We have to get a little fancy with this check, but yes, it is true. That is the correct answer. Pause the video and study the check if you wish. One final, very special example. Now, there are different ways to look at this. You could look at it as the difference between two cubes. You could look at it as the difference between two squares. If you paused the video and tried to work out either of those differences, as I encourage you to do, and you've come back here because you are extremely frustrated, I completely understand. The thing that would have made this simpler is to remove the greatest common factor first, because then you just have the difference between two squares to deal with. S plus 1, S minus 1. Enough said. Keep practicing the sum and difference of two cubes. Make sure you use soap for at least 20 seconds. Most of these problems will take longer than that. And I will see you in class.